Yeah. But I might do it. Like how they like that. I treat that on my one. So I'm gonna see you right here. Click on my sure see my teacher. I think I'm pretty sad. I gave the daughter your own money words. Josh and then I feeling something very good. He said he was like, oh, I really probably just. So back to my factory Saturday. Yeah. I didn't stretch like at all.
All right. So I finally justified why we need to multiply by t for when you have a repeated root. That I just in the past just said you had to multiply the second solution by t is like e to the 3t, but then also multiplied by t. The way you systematically justify that is by this method called reduction of order, where you take your solution to propose it to be built off of the first homogeneous solution. So you know this one's the one you're comfortable with. You know that e to the 3t must be one of them because r equals 3 is the root. But you use that times some arbitrary function of z. I mean, it's not arbitrary. We're going to find what it is that would force it to satisfy, force the solution to satisfy the differential equation. And it turns out that you get the full general solution where the other homogeneous solution does have a t multiplied. We also did the Euler equation where it's like t squared t, and so like these are non-constant coefficients, but they're of this specific form. And you'll get the solution for the root is 4, so one of them is t to the 4. The other one's actually t to the 4 with ln of t multiplied to it. And I justified that also using reduction of order, and you'll end up getting your general solution. So you build you're building your general solution as some v of t times your one of the homogeneous solutions, and then you can do this by plugging it in and forcing it to satisfy the differential equation to get the full general. You'll see the second solution has that. This one's not an Euler equation because this is a t and not a t squared, and then these are like plus ones that you shouldn't have. And this also shouldn't have a t if it's an Euler equation because the t should be only on the x prime, and this one's got a t with the x. So this is an equation that we don't know how to solve, but you could solve it using reduction of order so long as you're given one of the solutions. So I give you x of 1 is equal to e of t. And I mean, you wouldn't know that that's going to satisfy the differential equation, but maybe it's still worth checking. So you might check that x1 is e to the t is a solution. So why don't we just go ahead and do that? This should solve the ODE if you just plug it in. So it'll be t x double prime, let's e to the t. So the derivative is e to the t, second derivative is also e to the t. And then you'll have minus parentheses 2t plus 1. And then derivative e to the t is e to the t plus t plus 1. E to the t because you're just plugging x's up. And so if you multiply this out, so I'll just write the first term. This distributes, will be 2t e to the t. This to be minus e to the t plus t e to the t plus e to the t. Okay, so then this cancels with this. Okay, so this and this are going to be 2t e to the t, and then cancels with this. So they all cancel. Or maybe I'll make it like different colors, so you'll see that these actually cancel with each other. And so this is equal to 0, and that's good because this does satisfy the differential equation. This is a kind of equation that you wouldn't be able to, unless you stared at it long enough, maybe you could figure out that e to the t would be the solution for this. because it's not Euler, it's not constant coefficient, so you wouldn't be able to find it, but I'm just gonna give that to you. But the question is, what's the full general solution for this homogeneous equation? You need to have two homogeneous solutions because it's a second order equation, and you only have one. So what you do is you say the solution should be v of t times x1, and we're gonna find that v of t. Remember, this v, I say it's v of t, but I usually just like write v. It is a function of t, so you have to do the product rule when you actually plug into the differential equation. So we took this the first derivative, we took the second derivative, and then we were plugging this in. All the terms have e to the t, so I can just divide everything by e to the t. And once you divide everything by e to the t, and then let's just multiply out all these terms. So you have t v double prime plus 2t v prime plus tv. Then this you have to FOIL. So it'll be negative 2t v prime, 2t times, let's just do 2t times this. So it's going to have to be, well, there's a minus in the front. So that's why I'm going to have to do 2tv minus v prime minus v plus tv plus v. It's equal to 0. I'm going to underline all the v terms. This is a v term, v term, v term, a v term, and a v term. So there's 1, 2, 3, 4, 5 v terms. These should cancel. These will always cancel because if your solution, if you're using x1 as your homogeneous solution, this is always going to happen, and the book has a general proof for that. So the v and the v minus, the minus v and plus v cancel. There's a tv and a tv, but then there's a minus 2 tv, so these are all going to cancel. So I'll just go ahead and say not all the v prime terms will cancel, but at least these two will cancel. I'll use blue, green. So this is 2d v prime, 2t v prime. Those should cancel. Those aren't going to, well, we still have a v prime term here. So not all the v prime terms will cancel, but the v terms will always cancel. You have t v double prime, and then all this is gone, so it's just minus v prime. Okay, this is equal to 0. So we're going to have to solve for v, and then that goes into this v here. So let's reduce the order. So what we're going to do is, since all the v terms are gone, it's only v double prime and v. We're going to let w be v prime. And if you do that, then you're going to end up getting tw prime minus w is equal to 0. And then you could separate this. So I'll just do tw prime. I'm just going to write that as dw dt. So w prime is dw over dt. Move this to the other side, so it's equal to w. And I'm going to just divide both sides by t, and then multiply by dt, and then divide by w. So it should just be this after you separate them. Divide, multiply, divide. Then you just take the integral of both sides. And then we get, on the left, we get ln of absolute value of w is equal to the integral of t. 1 over t is just ln of t. Absolute value of t, but I'm just going to look at positive solutions. So t is greater than 0, so we'll have that. And then we'll have plus c because there's integration constants from both that you can consolidate. And I'll just note that this is absolute value of t is dropped because we're only looking at t is greater than 0. So let's take the exponential of both sides. That's going to give us absolute value of w is equal to e to the ln of t plus c. Then we can drop the absolute value, put a plus or minus, split this integral, this exponential to e to the c, and then, of course, the other one's e to the ln of t, but that e and the ln's will cancel, so you just have this. And then we'll just redefine this as a new coefficient, c1, call it c1. And we'll get that this is just c1t. Now, that's w. W is c1t, which means that v prime, so v prime is equal to c1t. So v is what we want, because that's like the v here. We're going to take the antiderivative, which means that v is equal to, it's like c1 over 2 t squared plus an integration constant c2, new integration constant c2. And of course, you can just say, well, c1 over 2 is just another arbitrary constant, so we'll just redefine that as c1. So you're left with c1 t squared plus c2. And then that's it, because your general solution is going to be built off of this v multiplied by your first homogeneous solution. So it's going to be this multiplied by x1, which was given as e of t, so we have that. And you can multiply this out. So you can say this is c1 t squared e to the t plus c2 e to the t. This was like the homogeneous solution that was given. And this turns out to be the homogeneous solution, the other homogeneous solution. It's just, I guess, the same one, but multiplied by t twice. So the idea is you can always get the full general solution, which means both homogeneous solutions, using reduction of order for any linear differential equation, even if you have non-constant coefficients, so long as you're given one homogeneous solution. You can always get the other one. And so this is an equation that otherwise you would not know the other homogeneous solution would be t squared e to the t. So let's do one more. Yeah.
With the dw equaling over w equals t over dt, is that supposed to be 1 over t, or why do we get ln t as the integral?
Oh, sorry. Yeah, that's wrong. Yeah, this is wrong. Yeah. This is dt over t, which is because you're dividing by t. Yeah. That's good. And so let's do one more. This one is also not an Euler equation. It's almost an Euler equation. What is breaking it from being an Euler equation? Let's see.
The plus one.
Yeah, it's this plus one. It should be like, because if you distribute this out, then basically, so because of this, not Euler equation. Really, if you were to write this out, it's really going to be t squared x double prime plus x double prime minus 2tx prime plus 2x is equal to 0. This is really what this equation is. And it doesn't have that. This term shouldn't be there. This x double prime shouldn't be there if you're going to have Euler equation. So you have a equation that's really like this if you end up multiplying it out. And this right here, this term is causing it to not be an Euler equation. So if you were to try to find the homogeneous solution, I mean, this is a homogeneous equation, so it's what you were trying to do is trying to find x1 both homogeneous solutions. You wouldn't be able to because it's not an Euler equation, but I'm gonna give you one of them. So I'll say like one of the homogeneous solutions is T. We could check. So we could say check that this is an actual solution. So x of 1 equals T solves the ODE. You'll have T squared plus 1. What is x double prime of T? It's just 0 because you'll take the derivative once, it'll be 1, and take the derivative again, it'll be 0. Minus 2t times x prime is 1 plus 2t. This is just going to be negative 2t plus 2t, which is equal to 0. So this works. And then using this homogeneous solution, you can build the general solution by saying that it's going to be sum v of t times x1, where our x1 is t. So then we're going to take the derivative. Of course, even though I wrote v like this, it's really a function of t. So you're going to have to do the product rule. You say v prime times t plus v, because the derivative of the second is just 1. And then you'll have your second derivative is equal to, take the product rule of the first term, x double prime t, plus v prime. But then there's a v prime, so it's going to be 2v prime. And then you're just going to plug it in. And so this t squared plus 1 is there, times this x double prime is this whole thing. And then you're going to minus this by 2t times this whole x prime term plus 2 times the vt, because that's the x is equal to 0. And I'll just underline the v terms right now. It's right here, and there's a v right here. Now, if you distribute it out, this negative 2t to this v, it would be negative 2tv, and this is 2v. They're going to cancel. These will cancel, and that's always going to be true, so long as you have the correct homogeneous solution and you did the product rule correctly. So then you're left with I'll just distribute this, so I'll just write it this way. Instead of foiling, I'll just do t squared plus 1 times this v double prime t. That gets distributed to this. And then I'll distribute this to this. So it's going to be t squared plus 1 to v prime. And then this is gone. There's only this term left on this one. It's going to be t squared. There's 2 t's, so it's going to be t squared v prime. It's equal to 0. And if you were to distribute out the 2v prime to this t squared, it's going to cancel with this. So I'll just say these two will cancel. And so we're left with t squared plus 1 v double prime t and then there's just a plus 2 v prime left equals 0. And now we don't have any v terms. You can reduce the order. You can't simplify this anymore. You can reduce the order of this. So we'll reduce the order by letting w equals v prime. Okay, so then you'll get t squared plus 1 times t. I guess I put the t out here, but I'm just going to put it out here in the front now. And then just say that's w prime, because this is v double prime, plus 2w is equal to 0. So we reduce the order to a first order equation. This is a constant coefficient first order differential equation, but it's separable, I believe. So if you took the w prime and made it dw over dt, so it'd be t squared plus 1t dw over dt. And then we can shove the other term to the other side, so minus 2w. All right, now you're going to divide by w, so it's going to be dw over dw. I'm going to multiply by dt, but divide, so it's going to become equal to negative 2 dt over the t squared plus 1 times t. This is separated now. This is separated. So now I could take the integral. The left side integral is really easy because that's just ln of w, absolute value of w. The right side integral is hard because it's like this t squared plus 1 times t on the bottom. And there's like well, the 2 on the top is not a big deal because you could pull that out. That one's harder. So like, but what do you think might be the integration technique for if you go back to Calc 2? What's like one thing that you'd have to do? Partial fractions. So there's like a partial fractions business going on with this one. And it's gonna be like a little distracting if I go and talk about that. It's probably take me like about 5 or 7 minutes to do the partial fractions. And that's not the point of the class. So I will do that because I have a second page here. So I'll post that. So you know, just know how to take the integral of something like this using partial fractions. But that's something that you can review. So after you do that integral, you'll get something that looks like this actually. So it's going to be there's a negative because there's a negative in the front of this, and then it's going to be like basically something ln of something minus ln of something, because it's going to be like taking the partial fractions. It's going to decompose this into like 1 over something plus 1 over something, and then it's going to become combined, and it's going to look like this t squared over t squared plus 1. So, and then of course there's an integration constant from both sides that you can consolidate to here, but I guess this integral here is equal to this essentially. But I'll show you how to do that. And then you can now take the negative and pull it up. So that's going to be nice because when I take the exponential of both sides, then I can get the e's and the ln's to cancel. So I'll pull it up. Then you'll just have ln of absolute value of w is equal to ln of t squared over t squared plus 1 raised to the negative 1 plus c. And then we're going to take the exponential of both sides. So, well, even before I do that, like it actually is easier to just do this actually. So let's just do ln of absolute value of w. If this is raised to negative 1, why don't we just do that right now? We could do it later, but I'll just do it now instead. If this is raised to negative 1, that's like taking the reciprocal of this. So I'll just say this is the same as t squared plus 1 over t squared. Okay, so now we don't have to have the negative 1 there. And then let's take the exponential. So then this will be absolute value of w because exponential of ln of absolute value of w. And then maybe it's quick enough to think about this as just e raised to all of this, but I always like split that exponential out. So it really is just going to be e to the c. I should have probably called this c1 because we're going to have a c2 later. And then, I mean, we'll do that. And then it's going to be e to the ln of the t squared plus 1 over t squared. And then we drop the absolute value, get a plus or minus e to the c1. These will undo each other. So this will just be multiplied by t squared plus 1 over t squared. And then we say this thing right here could be redefined as a new constant c1. And that leaves us with this is just equal to c1 times t squared plus 1 over t squared. But this is w, so you're going to have to say, okay, well, that means v prime. So I'll just say so v prime is equal to this thing. It may be easier, so we've got to take the antiderivative of this to get v. It may be easier to just recognize that this fraction can be split into two fractions. One fraction is be t squared over t squared, so that's just 1, plus the other one is 1 over t squared. That's the same thing. Because then it may be easier for you to take the antiderivative. So I'll just say, now we're just going to integrate this. So I'll just say this is integrate. So you'll get v is equal to c1 times what's the antiderivative of 1? It's just t. And what's the antiderivative 1 over t squared? It's like t to the negative 2, so you got to go to t to the negative 1, but then you have to compensate by multiplying by negative. So it's going to be t to the negative 1 plus another integration constant, because every time you take an antiderivative, there's another integration constant that comes out. So your that's it. That's your v. So your full solution is going to be x of t is built off of this v times your x1. X1 was t. You know, it's this red stuff right here. So it's going to be exactly just copying this is your v1, or this is your v, times your x1 is going to be t. So I'll do this is your v, whole thing, times x1 is t. And if you were to multiply this out, let's move this across here, then you'll have, so the t can get multiplied to each of these, so it's going to be c1 times t squared. And then, of course, t times t to the negative 1 is just 1. So this is the first term, and the second term will be c2 t. And that's your, so this was the homogeneous solution that was given to us, right? X of 1 is equal to t, and we checked that this actually does satisfy the differential equation. I think, you know, you would have not been able to know this one unless it was given to you. Then, now that you know this, you can find the general solution, including the second homogeneous solution, by reduction of order, and it turns out that the second homogeneous solution is actually t squared minus 1. And the sum of those two will be the solution to the homogeneous equation. And this looks like more work. There's actually even more work just because this blue box requires taking the integral of this thing, which requires using partial fractions, which I'm sparing us from seeing. Because this is like showing you what's new about this class. Of course, the integral of this blue box is going back, reviewing Calc 2. But I'll write it down here. It's like partial fractions. So that's how reduction of order works. Any question? So it's getting more involved only because now you have non-constant coefficients. So in the past, these were all just numbers, so we could just use a method of undetermined coefficients. But now that they're not numbers, the first case was Euler equation. That was a very special case of a non-constant coefficient. There's like so many different types of non-constant coefficients that you could have, but that was only if you had a t squared and a t precisely in front of the x double prime and in front of the x prime, and then no t, the last one had to be a constant. But if you start breaking that and having any kind of arbitrary non-constant coefficients on all the x double prime, x prime, and x is on the left-hand side, then you're limited to, you can't do any of those things. You have to, well, finding even one homogeneous solution would be difficult at that point. But if you are given one, then you can always use reduction order to find the general solution. But these have all been homogeneous. So if you notice, all of these had 0 on the right-hand side. So what if now you're saying your coefficients in front of your x double prime, x prime, all of those don't have to be constant, so they're going to be some arbitrary general functions of t. And on top of that, you make your right-hand side be not 0 anymore. In the earlier version of blank notes, I put A of t, B of t, and C of t here. But I decided I'll switch it to this because the book does it this way. And also, people in the past get confused that like, is A like the A from the characteristic or from the initial equation and all that. So we'll do it this way. And so a differential equation that has this makes it look like the coefficient in front of the x double prime has to be, cannot be, well, it looks like we're about to solve an equation where we can't have the coefficient in front of x double prime be a non-constant coefficient, but it turns out that those equations could be put in this form very easily. So like, for instance, you have these are non-constant in across all of these, but you can always just divide everything by t squared, and then you can get at least the first term, at least one of these terms, you can always make it equal to 1. So we'll do that in a moment. So this actually does capture all the types of second order linear non-constant coefficient differential equation with a non-zero right-hand side, because this f of t may not be equal to 0. So for solving this second order equation, so for reduction of order, you just needed one homogeneous solution, and then you propose that it's going to be v of t times that, and then you plug it in to find the v of t that will force to satisfy this differential equation. With variation of, so this is called variation of parameters, this method we're about to do. For solving non-homogeneous second order equation with non-constant coefficient, it turns out that you need both homogeneous solutions. So you'll need to first find both of them, need both homogeneous solutions. X1 and X2. And the solution is going to be built off of using both of them. So with variation of parameters, you just needed one of them, but with reduction order, you don't need one of them, but with variation of parameters, you need both of them. So x of t will be some function of v, I'm going to label that as v1 times x1, plus some function of v, another one, but it's not going to be necessarily the same. So I'm going to say this v1 is not going to necessarily be the same as this v2 times the other homogeneous solution. But keep in mind that these v1s and v2s are functions of t. They're general functions, t, v1. So we're going to have to find two functions, and then those multiplied by x2, x1, each of the homogeneous solutions added up together would be our solution form for a general non-constant coefficient, non-homogeneous differential equation. So what are we going to do? We're doing the same thing we did before. We're going to plug this into the differential equation to force it to satisfy it. And we're going to find a v1 and v2 that'll satisfy this differential equation once we plug it in. But do you predict that there's an issue? Like, how are we going to get two things from just one equation, right? Because you plug this in, you're going to have an equation that has v1 and v2 in it. That's just two things that you don't know and only one equation. So what we're going to do is we're going to come up with another equation that we're going to say should be satisfied, so that we can get two equations for two unknowns. We can't get away with just plugging this in. One of the equations for sure would be plugging this in directly and forcing it to satisfy it. But there's going to be another one that we're just going to say must be also satisfied. that one is is a little surprising that that would be okay to do. And I'm not going to justify that now. And if we have time, we can do it later because it's a little bit harder to justify. But I'll state it in a moment here. So when you try to plug this in, so we're going to plug this into this differential equation. Of course, you're going to take this first derivative of this, but each of these are products. So you got to do the product rule for this term and for this term. So we're going to do the first one is going to be V. We'll just do it this way. We'll say V1, and then we'll take the derivative of X1, plus I'll take the derivative of V1, and then write X1. Okay, so that's product rule across the first one. And then this one would be V2 X2 prime. And then this will be V2 prime X2. Okay. Yeah, good. So this is good. And then I'm just gonna rearrange this a little bit. So I'll just say I'll do V1 in the front. So I'll just do this V1 X1 prime, and then I'll take this term and say V2 X2 prime, and then I'll shove these other two here. So V1 prime X1 plus V2 prime X2. I just rearranged these, right? So they're just the same, but just rearranged. Let's see if I can fit it here. No, I can't fit it, so I'll just leave it. So what I'm going to propose is that I'm going to say that this right here is equal to, we're going to assume this right here will be 0. This looks like, what are you doing? We're thinking like V1 and V2 are like constants. So if we can maybe at this stage assume that V1 and V2 are constants, then V1 prime would be 0 and V2 prime would be 0. There won't be necessarily constants. We obviously didn't assume that when we took the product rule here, but I guess it looks as if we're going to assume that V1 prime and V2 prime will be constants here. But it's sort of like we didn't assume it first, and then we suddenly started to assume it. Because obviously, if we did assume V1 and V2 are constants, then the derivative of this would just be, of course, it would be just this. You just V1, X1, V2, X2. But it turns out that in general, even with this assumption, it won't always be constants. It'll be some functions of t. But the book says that this actually, so this means that we're going to have V1 prime X1 plus V2 prime X2 is equal to 0. So this is the other equation. So in practice, we need another equation. We're going to say this equation is what we're going to assume. We're going to assume that this is going to go away. And so we just say that we're going to pretend like V1 and V2 are going to be constants. They won't be necessarily constants. And we're not going to assume that when we take the next derivative. So when we take the next derivative, since we're going to say this is going to be 0, we're just going to take the derivative of this, but we're still going to do the product rule on this. So it's going to be V1 X double prime. And then you'll do the first derivative of V1 prime times X1 prime. And then you'll do V2 X2 double prime plus V2 prime X2 prime. So we're just pretending like it's a constant for the first derivative, but we won't pretend it for the second derivative. And the book says that this is like some ingenious thing that, you know, one can say and it doesn't cause us problems later. But there's actually something deeper, but I'm not going to look at that right now. We're just going to take this. There's a couple of things. We need two equations because there's two unknowns, V1 and V2. So just plugging this into the differential equation and forcing it to satisfy will give you only one. And so this is the other one we're going to say must be satisfied so that we get two equations for the two unknowns. And then if you don't have any issues, that's also you know, so we'll find that this doesn't cause us any issues. And that's what the book says, is that since this never causes issues, it looks like this is a good thing to use. But it doesn't really go into it beyond that. But we're still, that's only one of them. We still need to satisfy this equation. So we're going to plug this in. So x double prime is all of this. So plugging it in. So plug this in. That's x double prime plus p of t times x prime. Now that we said that this is going to be 0, it's just this. Plus q of t times the x is this thing. And this is going to equal your f of t. All right, so I'm going to underline all the x1 terms in blue. Okay, we'll do we'll do all the x1 I'll do all the v1 terms. I'll just do all the v1 terms. So let's do all the v1 terms. So this is a v1 term, this is a v1 term, and this is a v1 term. And then we'll do all the v2 terms. So this is a v2 term, this is a v2 term, and this is a v2 term. And so I'll consolidate. So I'll just say all these blue ones have a v1. And after you factor that out, you have x1 double prime. This one's p of t, x1 prime. And this one is q of t, x1. Plus all, so maybe I'll even make it with this color so people can see. So these were all the blue terms after you consolidate those. And then there's a v2. There's an x2 double prime. There's a pt x2 prime, and then a qt x2. And these were your orange underlined terms. Plus the rest is, so the rest is just the v1 prime x1 prime, and then there's this term right here, and that's it. So it's going to be plus your v2 prime x2 prime is equal to f of t. All right. So why did I do this? Is there something we know that this must equal to, this whole blue thing, as well as this whole orange thing? Keep in mind that x1, I'll just make it blue here, x1 and x2 are homogeneous solutions to this differential equation. Yeah, because if you think about it, if you're plugging in x1 into this one, and this one, and this one, given that x1 is a homogeneous solution, that's exactly the left-hand side. So this should be equal to 0. And same idea, this is x2 is also a homogeneous solution. So plugging it in, which is exactly what this is, should equal 0 because they're homogeneous solutions, which leaves us with just this right here has to be satisfied. So it leaves us with, I'll just copy it. This is your other equation. So we need two equations because they're two unknowns. This one makes total sense because it comes from just plugging it in. This one's a little sketchy because I'm just telling you that we're just going to assume this is equal to 0. And, you know, you might be like, why can we assume this is equal to 0? But we're just going to assume that. And we need another equation. And we're going to say, okay, we're going to have to pull another equation from somewhere. We're just going to say that is, we're going to think that's going to equal to 0. So v1 and v2 are going to act like constants here, although we actually don't assume it's constants because we're actually taking a product rule down here. But these are the two equations we need for both v1 and v2. Actually, your unknowns are v1 and v2 primes. You use these equations to solve for v1 and v2 primes, and then you'll take the antiderivative of both of those to find your v1 and v2, and those go into here. Okay, so But we could solve these kinds of equations using like Laplace transforms and other methods in later, and you'll find that this assumption doesn't cause any problems because it agrees with things we were going to do using other methods. But maybe it's worth also trying to see why this is why we could make this and it's not going to cause us problems. But for now, we're just going to say these are the two equations that V1 and V2 prime have to satisfy. So let's do a problem. So I'll say we're proposing our solution to this equation is going to be of this form. Okay. This is an Euler equation if you just look at the left-hand side, but all the Euler equations we've done, it's always been zero. It's always been like a homogeneous equation. So now we're doing Euler with a non-homogeneous, so you have to use variation of parameters. So would propose our solution is going to be this. We need two homogeneous solutions, right? So the variation of parameters requires you to find two homogeneous solutions because you build the solution, general solution from that. So you'll do the initial equation because this is the Euler equation. This becomes r squared minus 4r plus 3. And this factors to r minus 1, r minus 3 equals 0. So therefore, your r is equal to 1 and 3. So your x1 is equal to t. Remember Euler's equation, the solutions are t raised to the r, and there's two distinct ones. So you have t and t cubed. And so what were the two equations that we needed to satisfy? It was, one of them was this. I'll grab this. Grab this one. And the other one was this. And I'll just make them both blue and then just say this is the system of, they're just algebraic equations if you think of your unknowns as being V1 prime and V2 prime. And then you can plug in the x1 and x2. So it's going to be V1 prime times t plus V2 prime times t cubed is equal to 0. And then the other one is V1 prime times, well, what is x1 prime? This is x1 prime. That's just 1. Plus, then the other one is V2 prime times what is x2 prime? That's the derivative of this. So it'd be 3t squared is equal to, and what is f of t? So this one, this is where you have to be careful because this, what we did up here, we derived all of this assuming that there's a 1 in front of this x double prime, right? So we're going to have to convert this equation to having 1 in front of the x double prime. So if you divide everything by t squared, it's going to be x double prime minus 3t to the negative 1, x prime plus 3 to the t to the negative 2. X is equal to 4, t to the 7, but minus 5, so be t to the 5. So that's your f of t. This is your f of t because the formulas we had derived up here started with there being a 1 in front of the x double prime. So you have to convert this equation to have only a 1 in front of this x double prime. So that means you're just dividing everything by t squared. These middle terms don't really get used anyway, so you could just go straight and just say, I'm just take the t to the 4t to the 7th and divide it by t squared, and you'll just get this. This is a system of equations for V1 prime and V2 prime, and we're just going to solve that, and you'll get V1 prime and V2 prime, and then anti-differentiate, and then those go into these two spots, and that's your general solution for this non-homogeneous differential equation. So we'll do that next time. Yeah, so we'll probably have like, hopefully one class will get through most of the variation of parameters. it's hard, it's a little harder, right? So things are harder for this.
What are you gonna be tested to?
The just electrical circuits inclusive.
Okay.